We're going to take a look back at some applications of derivatives, specifically at where things are increasing or decreasing or have relative extrema, and also at concavity and points of inflection. So the first thing that I have here is a reminder of a theorem dealing with increasing or decreasing. If a derivative is positive, greater than 0 or positive, then the function is increasing on that interval. If the derivative is less than 0 or negative, then the derivative is decreasing on that interval. If the derivative is equal to 0, then f is constant on that interval or at that point, so it's not increasing or decreasing. First thing that we needed to do whenever we were trying to check these things, as far as relative minimum and relative maximum, those are referred to collectively as your relative extrema. If your derivative changes from negative to positive, then that's a relative minimum. If derivative changes from from positive to negative, that's a relative maximum. If we have the exact same sign on both sides of that point, then it is not a relative minimum or a relative maximum. Okay? And that's where sometimes we can have points where the derivative is equal to 0, but it's not a relative extrema. It's just a horizontal tangent. Okay, now, concavity and points of inflection. If your second derivative is greater than 0 or positive, then the original function is concave up on that interval. If the second derivative is less than 0 or negative, then the original function is concave down on that interval. If the second derivative is changing signs, either way, doesn't matter which way, negative to positive or positive to negative, then that is a point of inflection. Okay? Let's take a look at an example. We're going to do everything with this one. Okay, so I'm going to scroll down a little bit so we have plenty of room. Find the intervals where f is increasing or decreasing, concave up or down, and x coordinates of any relative extrema or points of inflection. Okay, so let's get started on this one. We want to see where all of these things are happening. So let's start with increasing, decreasing, and relative extrema, because that's what happens. That's what we're looking at when we look at first derivative. So let's take that derivative. 4 times 1/2 gives us 2. So we have 2x cubed plus 3 times 2 gives us 6x squared. Set equal to 0 to find those critical numbers. We could take out a 2x squared, and that leaves x plus 3. So now we have x equals 0 and x equals negative 3 as our critical numbers. Let's make a quick little number line for the derivative. So let's plug in something to the left of negative 3, say negative 4. We're going to have a positive on the outside and a negative on the inside, so that would be a negative. Something between negative 3 and 0 would be negative 1. Positive on the outside, positive on the inside, so that's a positive. Something to the right of 0 would be positive 1. Positive on the outside, positive on the inside, that's another positive. So we now know this function is increasing between negative 3 and 0, and when x is greater than 0. Now, some of you may be asking, why did we not write that as a single interval? The reason for that is we know that the derivative is equal to 0 at 0, so that means it's not increasing or decreasing there. So we can't include that in the interval. Decreasing, where our derivative is negative, is when x is less than negative 3. And then relative extrema, let's see, we only have one. At negative 3, we can see our derivative is changing from negative to positive, so that is a relative minimum at x equals negative 3. Now notice this just said find the x coordinates, right? Okay, x coordinates. So we did not have to plug back in. If they had said find the points or all the coordinates, then that would be plugging back into the original function to find the y coordinate. Okay, just so we know. All right, now let's take a look at second derivative and what that can tell us. Derivative of 2x cubed plus 6x squared is going to be 6x squared plus 12x. We want to set equal to 0. We can take out a 6x, and that leaves x plus 2. So that gives us 0 and negative 2 as our numbers. Let's make a quick little number line. for second derivative. Okay, something to the left of negative 2 would be negative 3. If we plug that in, we're going to have a negative times a negative, which is a positive. Between negative 2 and 0 would be negative 1. If we plug that in, we're going to have a negative times a positive, which is a negative. And then something to the right of 0 could be 1. If we plug that in, we're going to have a positive times a positive, which is a positive. So we now know that our original function is concave up, where the second derivative is positive, which is when x is less than negative 2 and when x is greater than 0. We also know that the original is concave down, where the second derivative is negative, which is in between negative 2 and 0. And then the last thing we can find from this are our points of inflection. Second derivative is changing signs at two different places at both x equals negative 2 and x equals 0. And again, we only had to find the x coordinates. Make sure you pay close attention to what a question is asking you to do so that you have answered it fully. Make sure you know whether you're supposed to find just x coordinates or you're also supposed to find the y coordinates. Okay. The next thing that I want to talk to you guys about, this is a cool little, just a little graphic organizer for the differences between what we say when we're talking about a position function and what it means for actual motion, okay? So a lot of times we're doing the same things. We may be finding a first derivative and evaluating where it's positive or negative, but instead of saying where is this increasing, where is this decreasing, we might be asking how is the particle moving or how is the object moving? Is it moving left, right, or up or down, depending on what kind of axis it's moving along. So again, this is just to kind of talk about what this looks like as far as we might be doing the same thing, but how is it going to be worded when we're talking about motion? So value of a function at x is what we normally think of, but with motion, we're looking at position at time t, right? The original function is position. First derivative x prime of t, well, the derivative of position, derivative of x of t or y of t is velocity v of t. Second derivative is your acceleration, which is also derivative of velocity. Here's what we were talking about for just a minute ago, increasing or decreasing. Instead of saying where is the function increasing, we might be saying where is the function moving to the right or up, depending on which axis it's moving along. And instead of saying where is the function decreasing, we might be saying where is the particle or object moving to the left or down, depending on which axis it's on. Remember, if we see the words where's the particle at rest, that's asking for where the velocity, which is the first derivative, is equal to 0. If they ask us where the particle, changes direction, then that's talking about where velocity, which is the first derivative, is changing signs. So that'd be setting up a sign chart like we would normally do to find relative extrema, except we're talking in motion about where it's changing direction. Something that we may not have talked very much about in Calc Honors, the speed of a particle or an object is the absolute value of velocity. So speed is always going to be positive, or it could be 0, but it's never going to be negative. All right. Next, we sometimes are asked questions where they will say, is the speed of the particle or object increasing or decreasing at this value? So here's what I want you to kind of, a little bit easier way to write this out. Instead of saying speed is increasing, decreasing, and the positive and decreasing signs, that's just too much to kind of keep in mind. So here's what I want you to think about, okay? Speed is increasing, okay, when velocity and acceleration have the same sign. Okay, so whether that's positive or negative, if they're both positive or they're both negative at that value, then speed is increasing. Okay, and that's an easier way to remember that. Speed is decreasing when velocity and acceleration have opposite signs. Okay, so that's just a little note you might want to jot down. We do see these problems sometimes, especially as a piece of a free response. That's usually where that shows up. It'll ask if speed is increasing or decreasing. And so you want to take a look at the values of velocity and acceleration at that specific t value. Okay, if they have the same sign, then the speed is increasing. If they have opposite signs, then the speed is decreasing. Okay, and you can see that over to the left. Notice when I said when speed is increasing for both of those, either they're both positive or they're both negative. Okay, when speed is decreasing, they have opposite signs. Okay, but it's just a quicker way to recognize rather than saying, okay, well, looking at, well, when velocity is negative and acceleration is positive, again, just remember same sign or opposite signs. That's a lot faster to memorize. And I'm going to have a little graphic of this for you guys to download if you would like for the particle motion to have. All right, let's take a look at particle motion. We're going to go through an example. We'll see how much space I've got to write everything down that I might need to. Position in centimeters of a particle traveling along the x-axis is modeled by this function, x of t, where t is time in seconds and t is greater than or equal to 0. Guys, super important, because a lot of times we'll get a negative answer for t and we can't use that, but people will forget and put it in a free response anyway. For part A, at what times is the particle at rest? So remember what we just said in our graphic before. At rest means velocity equal to 0, first derivative equal to 0. So we need to take that derivative to find velocity. We would get 3t squared minus 13t plus 4. Now we want to set this equal to 0. So we could factor. What would that give us? We'd have 3t and we'd have t, and then minus 1 minus 4. There we go. So we get the values t equals 1/3 and t equals 4, both of which are positive, so that works. Okay, so we are at rest at 1/3 and 4 seconds. Part B, when is the particle moving to the left? Okay, this is the same thing as we would think of as decreasing on our applications of derivatives. So let's set up our number line. We already have our values, 1/3 and 4. And remember, just as a little reminder out here, we're starting at 0, right? So we can't go beyond that. So let's think about plugging in something between 0 and 1/3. We could plug in 1/6. If we plug that in, we are going to end up with a positive, because we would have a negative times a negative. Let's plug in something between 1/3 and 4. Let's plug in 1. We're going to have a positive times a negative, which is a negative. And then something bigger than 4, let's plug in 5. We're going to have positive times a positive, which is positive. Okay, so when is the particle moving to the left would mean when is the velocity negative. So first derivative is negative on this number line between 1/3 and 4. Something that I also want to make sure that we talk about really quick. Notice that my variable here is t. So I do not want to put an x in my interval, because x in this case is the position. So if I wrote 1/3 is less than x is less than 4, it's wrong, because the variable here is t. We're talking about time. So make sure we get used to that. Find the position of the particle when its acceleration is 0. Okay, so what we need to do here, we need to find acceleration first of all. So we got to take derivative of velocity. So we're going to have 6t minus 13. And we want to know where that's equal to 0. So that would be at t equals 13 over 6. Now we need to plug that into position. Okay, and our position function, again, just as a reminder up here, position function was t cubed minus 13 over 2 times t squared plus 4t minus 8. Now we want to plug in 13 over 6 for that. This is one where you would probably have the calculator, obviously. You don't want to be cubing 13 on your own. So you can use your calculator. I'll scroll back up so you can see it. You can use your calculator to plug in 13 over 6. If we do that as a fraction, it's 1123 over 54, which is as a decimal. Oh, nope. Sorry. Wrong spot. It's negative 2125 over 108, which is approximately, as a decimal, negative 19.676, and we are in centimeters for position. Okay, guys, really quick. Also, just a reminder, anytime you have decimals, you want to make sure that you are rounding to the third decimal place. Always. You can round or truncate, which means you can round up if you need to, or you can just cut it off. But you always want to go 3 decimal places. Okay. They are a very big stickler about this on the AP exam. If you don't go those 3 decimal places, you do not get credit for the answer point. So make sure you're going 3 decimal places anytime you have a calculator question. Now, if it's something where it's 5 divided by 2, which is 2.5, you can leave it as 2.5. But if it keeps going, you want to go to 3 decimal places. Okay, so next, we want to find total distance from 0 to 3. So here's what we need to know. Between 0 and 3, we've already said up here, whoops, not here, not in A, in part B, that we know we're moving from the left between 1/3 and 4. That means we're changing direction at 1/3, right? Which is in between 0 and 1. So we need to find x of 0, x of 1/3, and x of 4. Position at all 3 of these places so that we can find the total distance. Position at 0, that's easy. Plug in 0, we would get -8. Position at 1/3 is negative 397 over 54. Position at 3, or excuse me, why did I say 4 earlier? Okay, let's see what I can do about this. Let's just mark that out. Make this a 3. Goodness. Position at 3 is negative 55 over 2. So now we need to find distance in between. Distance in between -8 and negative 397 over 54 is 35 over 54 units. Position between negative 397 over 54 and negative 55 over 2 is 544 over 27 units. Okay, so if we add these two together, that's going to give us our total distance. Okay, that's around negative 7.325 or 352 and negative 27.5 for these original coordinates. If you did them as a decimal, that's fine. So when we add these up, this is where I wrote down the wrong answer to begin with for part C. 1,123 over 54 centimeters, or as a decimal, that is 20.796 centimeters is the total distance. Now, if we don't take that into account, we're not going to get the right amount. Okay, if we don't take that into account, we're only going to be looking for the distance between -8 and the negative 27.5, which is not the 20.796. We have to take into account the fact that this is changing direction. Okay, which we've already talked about before, but I just wanted to make sure to reiterate. Okay, here's another free response. This time we are dealing with trig, so we'll try to go through this one pretty quick. It's a little bit shorter in what you have to do. Part A, we want to know at what time is the particle at rest. Notice this one's going along the y-axis, so it's y of t. So in order to get where something's at rest, we want to know where velocity, which is first derivative, is equal to 0. So v of t, take derivative, 1 minus 2 times sine of t. Let's set it equal to 0. So we're looking for where sine of t is -1 over -2, which would be positive 1/2. So let's think about our values here. Where is sine equal to positive 1/2? That's going to happen at pi over 6 and 5 pi over 6. Okay, so those are our answers here. And let's see, did they give us units for t? Yes, seconds. Okay, so part B, when is the particle moving up? Okay, this is like asking when is the function increasing, because if it's moving up, then the derivative is going to be positive. Remember, velocity implies direction. So let's set up our number line, pi over 6 and 5 pi over 6. Again, remember, we're only between 0 and 2 pi, so it might be good to include those as the endpoints because we can't go beyond that. If we plug in to the left of pi over 6, we're going to get a positive. Between pi over 6 and 5 pi over 6, we would get a negative. And then between 5 pi over 6 and 2 pi, we would get a positive. All right, so when is the particle moving up? That's when the velocity is positive. So between 0 and pi over 6, and between 5 pi over 6 and 2 pi. Guys, for me, I think it's also a good reminder to put those on your number line, because that way when you go to write your intervals, you don't forget that you're starting at 0 and ending at 2 pi. Next one, find velocity of the particle when its acceleration is first equal to 0. Okay, a lot of times you'll see these with designating when it's first equal to 0, because remember, trig functions are periodic, so they're going to repeat solutions. Let's find acceleration, which would be the derivative of velocity. Derivative of 1 minus 2 sine of t is going to be negative 2 cosine of t. Let's set that equal to 0. So we're looking for where cosine is equal to 0. The first time that happens on our interval 0 to 2 pi is at pi over 2. So now we want velocity at pi over 2. So 1 minus 2 sine of pi over 2, 1 minus 2 is negative 1. Units for velocity, remember, it's the position units divided by time, so inches per second. All right, I've also got some multiple choice for you guys to take a look at. Position of an object attached to a spring is given by that function there, where t is time in seconds. In the first 4 seconds, how many times is the particle at rest? Guys, this is a calculator active question, okay? So we're going to use the calculator. First, we're going to find velocity, because we want to know when it's at rest. So let's find velocity, okay? Take derivative of 1/6 cosine of 5t. Okay, we're going to have negative 5/6 sine of 5t. Derivative of negative 1/4 sine of 5t is going to be negative 5/4 cosine of 5t. Okay, using chain rule there for trig. Now, what I would do with this, graph this function. Okay, and you can graph it using x's, okay, in your graph, and make your window from 0 to 4, because notice that this says in the first 4 seconds. So change your window to be from 0 to 4. Now, we are only interested in where it's at rest, so where it's touching 0. So you could change your y min and max to like negative 2 and 2, so that you're only looking really close to the x-axis. If we take a look at that graph in the first 4 seconds, velocity is equal to 0 6 times. Okay, number 2. Particle moves along the x-axis, so its position is given by this function here. At what time is the particle at rest? Okay, remember, at rest, we want velocity equal to 0. This is definitely one that you would be expected to be able to do without a calculator. Let's take that derivative. We're going to have 6t squared minus 42t plus 72. We want to set equal to 0. We could take out a 6 from everything. That would give us t squared minus 7t plus 12. Now we can factor easily. Okay, t minus 3, t minus 4. So t is equal to 3 and t is equal to 4. Both of these are positive answers, 3 and 4 seconds. Okay, that should be pretty easy. Okay. Next one is definitely, obviously, a calculator active question, because your answers are in decimals. So definitely a calculator active question. Let's take a look. Velocity given by this function. What's the acceleration at t equals 4? So let's find the acceleration function. Derivative of 3 just goes away. Derivative of 4.1 cosine of 0.9t. Well, we know we're going to have a negative sign, and we also are going to have to multiply the 4.1 by derivative of what's inside here, which will be 0.9. So 4.1 times 0.9 is going to be 3.69. So this derivative is negative 3.69 sine 0.9t. Now we want to plug in 4. So negative 3.69 times sine of 0.9 times 4. Okay, guys, on your calculator, make sure you are in radian mode. Everything we do will be in radian mode. There will not be a single thing where you will have to change that. We will always be in radian mode on our calculators. When we do that, we should get 1.633. Okay, those were just a couple multiple choice. We will do quite a bit more multiple choice throughout this unit and beyond. So hopefully that was a good refresher of some of your applications of derivatives.